Here's what NASA won't tell you. We're never leaving. The cosmos isn't waiting for us with open arms. It's a hostile wasteland designed to kill us. The prison bars keeping us trapped on Earth aren't made of metal. They're made of physics, biology, and distances so vast they mock our every attempt to escape. Here is a question. If you could leave Earth right now and visit any place in our galaxy, where would you go first? Comment down below. I'll pin the most creative answer. Now let's begin. We've always been explorers. From the moment our ancestors looked beyond their caves, we've been driven to discover what lies over the next horizon. We crossed oceans, climbed mountains, and eventually sent 12 human beings to walk on another world. The moon landings weren't just technical achievements. They were proof that we could escape Earth's gravity well and plant our feet somewhere new. But that was over 50 years ago. Since 1972, no human has ventured beyond low Earth orbit. Why? You might think it's about money or political will, and those factors certainly play a role, but there's something deeper, something more fundamental holding us back. The universe operates on rules that don't care about our ambitions or our dreams. These rules are written in the fabric of space-time itself, encoded in radiation fields that permeate the void and expressed through biological limits that evolution never prepared us for. When we look at the cosmos through our most powerful telescopes like the James Webb Space Telescope or the Hubble Space Telescope, we see galaxies billions of light years away. A light year is the distance light travels in 1 year, moving at roughly 300,000 kilometers per second. That's fast enough to circle Earth 7.5 times in a single second. Yet even at that incomprehensible speed, light from distant galaxies takes billions of years to reach us. The Andromeda Galaxy, our nearest large galactic neighbor, sits 2.5 million light-years away. If you left Earth today traveling at the speed of light, you wouldn't arrive there until 2.5 million years from now. To actually reach light speed would require infinite energy, which is impossible. The fastest human-made object ever created is the Parker Solar Probe, launched in 2018 to study the Sun. At its peak velocity, it reaches about 430,000 miles per hour. That sounds incredibly fast until you realize it's still only about 0.06% the speed of light. At that rate, reaching Proxima Centauri, the nearest star system to our Sun at roughly 4.2 light-years away, would take thousands upon thousands of years. Even if we could somehow approach light speed, relativistic effects would create bizarre consequences. Time dilation means that time passes differently for someone traveling near light speed compared to someone stationary. You might experience a journey of a few years, but centuries would pass back on Earth. Everyone you knew would be gone. Human civilization itself might have transformed beyond recognition or ceased to exist entirely. You'd be traveling not just through space, but through time, becoming a relic from a distant past, arriving in an unknowable future. Now imagine we solved the speed problem. Imagine we invented some revolutionary propulsion system, perhaps nuclear thermal propulsion, or even theoretical concepts like antimatter engines or warp drives. We'd still face another monumental challenge: radiation. Space is not the empty void we once imagined. It's filled with high-energy particles traveling at near light speed, cosmic radiation that can slice through metal, electronics, and human tissue like invisible knives. There are two main types of space radiation we need to worry about. First, there's solar radiation, particles ejected from our Sun during solar flares, and coronal mass ejections. These events can release billions of tons of charged particles into space. During a major solar storm, astronauts outside Earth's protective magnetic field could receive a lethal dose of radiation in hours. Then there's galactic cosmic radiation, or GCR, which comes from outside our solar system. These particles, primarily protons and heavier atomic nuclei, are accelerated to incredible energies by supernova explosions and other violent cosmic events. They're traveling so fast and carrying so much energy that they can penetrate spacecraft hulls, spacesuits, and the human body itself. Here's something truly terrifying. When these high-energy particles strike matter, they don't just pass through cleanly. They create secondary radiation showers, cascades of particles that can actually make the radiation environment inside a spacecraft worse than outside. Studies conducted by NASA's Human Research Program reveal that astronauts on long-duration missions to Mars could face radiation exposure levels that significantly increase their lifetime cancer risk. We're talking about doses that could exceed NASA's current permissible exposure limits designed to keep astronauts as safe as possible while acknowledging the inherent dangers of space exploration. Research published in NASA Technical Reports shows that galactic cosmic rays can damage the central nervous system, potentially causing cognitive impairment, memory problems, and behavioral changes. Imagine traveling for months or years through deep space, only to arrive at your destination with your mind compromised, your memories foggy, your ability to think clearly diminished. You'd still be you, but a damaged version, a shadow of who you were when you left Earth. And there's currently no perfect solution. Shielding helps, but adding enough shielding to significantly reduce GCR exposure makes spacecraft prohibitively heavy and expensive. Some materials actually make the problem worse by creating more secondary radiation. If you're finding this fascinating and want to explore more cosmic mysteries, hit that subscribe button and give this video a thumbs up. Your support helps me bring these stories of the universe to you. But radiation is just one piece of the puzzle. Let's talk about what space does to the human body itself. We evolved over millions of years in Earth's one-gravity environment. Our bones, muscles, cardiovascular system, even the fluid pressure in our eyes are all calibrated for this specific gravitational pull. Remove that gravity and our bodies begin to break down in ways that are both predictable and deeply troubling. Astronauts on the International Space Station, which orbits just 400 kilometers above Earth's surface, experience microgravity. Within days, they start losing bone density at rates similar to someone with severe osteoporosis. They lose roughly 1 to 2% of their bone mass per month in space. Their muscles atrophy, weakening even with hours of daily exercise using specialized equipment. Fluids shift upward in their bodies, causing their faces to puff up and creating pressure behind their eyes that can damage vision, a condition researchers call spaceflight-associated neuroocular syndrome. Their immune systems become compromised, making them more vulnerable to infections. Research published in the journal NPJ Microgravity in 2024 describes how the human immune system faces profound challenges after leaving Earth. Pro-inflammatory responses increase, latent viruses like herpes and chickenpox can reactivate, and the body's ability to fight off diseases diminishes. To make matters worse, bacteria and other microorganisms become more virulent and drug-resistant in space. They literally become more dangerous while our ability to fight them off gets weaker. Now picture this scenario: you're on a spacecraft heading to Mars. The journey takes roughly 6 to 9 months one way, depending on the planetary alignment. That means you're spending at least a year and a half in microgravity for a round trip, and that's assuming everything goes perfectly. By the time you arrive on Mars, your bones are brittle, your muscles weak, your immune system compromised, and your vision potentially damaged. And Mars itself only has about 38% of Earth's gravity. That's better than zero gravity, but it's still not enough to stop the deterioration. You'd need to spend years recovering after returning to Earth, assuming your body could fully recover at all. Some researchers have proposed using rotating spacecraft to create artificial gravity through centrifugal force. Picture a giant wheel spinning in space with the rotation pushing everything toward the outer rim, simulating gravity. It's a beautiful concept that's been featured in countless science fiction stories. But building such a structure would be enormously expensive and technically challenging. the engineering required to create a rotating section large enough to avoid causing motion sickness, strong enough to withstand the rotational stresses, and reliable enough to operate for months or years without failure is staggering. We haven't built anything close to this scale yet. Then there's the psychological dimension. Imagine being sealed inside a metal container no larger than a small apartment with the same handful of people for months on end. You can't go outside, you can't feel the wind on your face or smell fresh air. You can't call your family whenever you want because radio signals take minutes to travel between Earth and Mars, making real-time conversation impossible. The isolation, the confinement, the knowledge that any major malfunction could mean certain death, all of this creates psychological pressure that few human beings have ever experienced. Studies on long-duration spaceflight and analog environments like Antarctica research stations show that crew members can experience depression, anxiety, interpersonal conflicts, and cognitive decline. There's nowhere to escape, nowhere to go when you need space from your crewmates. One major disagreement could jeopardize the entire mission. One person's psychological breakdown could endanger everyone. NASA's behavioral health research emphasizes that these aren't minor concerns. They're mission-critical challenges that could determine whether deep space exploration succeeds or fails catastrophically. But let's assume we somehow overcome all these obstacles. We develop better propulsion systems, advanced radiation shielding, artificial gravity, comprehensive medical countermeasures, and rigorous psychological support. We successfully send humans to Mars and establish a small outpost. What then? Can we truly colonize another world and make it a second home for humanity? Mars seems like the most obvious candidate. It has a day length similar to Earth's, roughly 24 hours and 37 minutes. It has polar ice caps containing water ice. Its surface shows evidence of ancient rivers and lakes, suggesting it once had a thicker atmosphere and possibly conditions suitable for life. But present-day Mars is a frozen desert with an atmosphere less than 1% as thick as Earth's, composed mostly of carbon dioxide. The average temperature hovers around -63 degrees Celsius. The atmospheric pressure is so low that liquid water cannot exist on the surface. It either freezes solid or evaporates instantly. Anyone living on Mars would need to stay inside pressurized habitats essentially all the time. Every excursion outside would require a spacesuit, a personal spacecraft you wear on your body. A single tear in that suit, a single seal failure, and you'd have seconds before losing consciousness and minutes before death. You couldn't grow food outside because of the cold, the low pressure, the lack of breathable air, and the intense ultraviolet radiation that bombards the surface. You'd need to grow everything in controlled indoor environments using artificial lighting, carefully recycled water, and imported or synthesized nutrients. Speaking of resources, everything you need would either have to be brought from Earth at enormous cost or manufactured on Mars using local materials through a process called in situ resource utilization. A 2024 scientific paper analyzing SpaceX's plans for Mars colonization using their Starship vehicle found significant technological gaps and concluded that current proposals don't yet provide a feasible return flight scenario. The mass of required life support systems, propellant production equipment, power generation, radiation shielding, and other necessities exceeds what we can currently transport and maintain with existing or near-term technology. And here's something that keeps scientists awake at night. We don't know if humans can successfully reproduce in reduced gravity. We have no data on whether pregnancy, fetal development, and childbirth can occur normally in Mars gravity. If they can't, then any Mars colony would be completely dependent on a continuous supply of new colonists from Earth. It wouldn't be a true second home for humanity. It would be an outpost perpetually reliant on the mother planet for its survival. If Mars is the best option in our solar system and it's this challenging, What about the rest? Venus has a thick atmosphere, but the surface temperature reaches 460 degrees Celsius, hot enough to melt lead. The atmospheric pressure at the surface is 90 times that of Earth, equivalent to being a kilometer underwater. Sulfuric acid clouds fill the sky. Some scientists have proposed floating cities high in Venus's atmosphere, where temperatures and pressures are more Earth-like, but you'd be living in a balloon city suspended above a hellish surface with no land to stand on and no local resources to access except atmospheric gases. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are gas giants with no solid surface to land on. Their moons are more interesting. Europa, a moon of Jupiter, has a subsurface ocean beneath its icy crust that might contain more liquid water than all of Earth's oceans combined. Enceladus, a moon of Saturn, similarly, has a subsurface ocean and geysers that spray water into space. These are fascinating places to search for life, but they're also incredibly distant and bathed in intense radiation from their parent planets. Jupiter's radiation environment is so extreme, it would kill an unshielded human in days. This might be a good moment to mention something related. I made another video exploring why the universe might be full of dead worlds, places that once had life but lost it due to cosmic catastrophes or environmental collapse. If you're intrigued by that possibility and want to understand more about why finding living worlds might be so rare, the video is in the description and on the card above. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane and ethane on its surface. It's a fascinating place, but the surface temperature is minus 179 degrees Celsius. There's no oxygen to breathe. You'd still need a full life support system and heated habitats. And Titan is roughly 9.5 astronomical units from the Sun, meaning it receives about 1% of the sunlight that Earth receives. Solar panels would be nearly useless. You'd need nuclear power for everything. Every potentially habitable location in our solar system has deal-breaking challenges. None of them offer anything close to Earth's combination of breathable atmosphere, liquid water, moderate temperatures, protection from radiation, and abundant resources. Earth is a paradise compared to every other world we've found. And this brings us to a profound realization. We're not adapted to live anywhere else. We're Earth creatures, products of billions of years of evolution in this specific environment. Our bodies, our biology, our very existence is tailored to this one planet orbiting this one star in this one region of space. But what if we look beyond our solar system? What if we accept that our cosmic neighborhood offers nothing truly habitable and set our sights on exoplanets, planets orbiting other stars? After all, astronomers have discovered thousands of exoplanets in recent years using telescopes like Kepler, TESS, and now the James Webb Space Telescope. Some of these worlds orbit within their star's habitable zone, the region where temperatures could allow liquid water to exist on the surface. Surely some of them must be Earth-like enough to support human life, right? Here's where the distance problem becomes truly insurmountable. The nearest confirmed exoplanet in a potentially habitable zone is Proxima Centauri b, orbiting the red dwarf star Proxima Centauri approximately 4.24 light-years away. That's about 40 trillion kilometers. If we sent our fastest current spacecraft, the Parker Solar Probe, traveling at 430,000 miles per hour, the journey would take roughly 6,000 years. 6,000 years ago, humans were just beginning to develop agriculture and build the first cities. Imagine launching a mission that would take that long. Everyone involved in planning and launching it would be dead for millennia before it arrived. Entire civilizations would rise and fall during the journey. Even if we dramatically improved our propulsion technology, perhaps using nuclear pulse propulsion or fusion drives that could reach several % of light speed, we're still talking about journey times of decades to centuries. You'd need a generation ship, a spacecraft large enough to support a self-sustaining population for multiple human lifetimes. The engineering challenges are mind-boggling. You'd need to create a completely closed ecological system that could recycle air, water, and nutrients with near-perfect efficiency for centuries. Any inefficiency, any loss of resources, compounds over time until the system collapses. You'd need enough genetic diversity in your population to avoid inbreeding problems over multiple generations. You'd need to maintain complex technology for centuries without access to Earth's industrial base or supply chains. A single critical component failure that you couldn't repair or manufacture could doom the entire mission. You'd need social structures stable enough to prevent conflicts, mutinies, or cultural breakdown over timescales longer than most human civilizations have existed. And all of this assumes you know where you're going and that the destination planet is actually habitable when you arrive. Here's something sobering. We can't actually see the surface details of exoplanets. They're too far away and too small. Even our best telescopes can only detect them indirectly by measuring the slight dimming of a star as a planet passes in front of it, or by detecting the tiny wobble a planet's gravity causes in its star's motion. We can analyze the light passing through an exoplanet's atmosphere during these transits to identify chemical signatures of gases like water vapor, methane, or oxygen, but we can't see if there are oceans, continents, or breathable air at the surface. We can't detect magnetic fields that might protect against radiation. We can't know if the planet is geologically active, tidally locked, or subjected to violent stellar flares from its parent star. Proxima Centauri b, that nearest potentially habitable exoplanet, orbits a red dwarf star. Red dwarfs are the most common type of star in our galaxy, which sounds promising for finding habitable worlds. But they're also prone to frequent, powerful stellar flares that could strip away a planet's atmosphere and bathe the surface in lethal radiation. Proxima Centauri itself has been observed producing flares that increase its brightness by factors of 60 or more. Any life on a planet orbiting so close to such a temperamental star would face existential threats regularly. And even if we found a perfect Earth twin, a planet with the right size, the right temperature, the right atmosphere, liquid water oceans, and protective magnetic fields, we'd face another profound challenge: alien biology. If that planet has life, which is likely if conditions are truly Earth-like, that life would have evolved completely independently from Earth life. It would have different biochemistry, different molecular structures, potentially different fundamental building blocks. Earth life uses DNA and RNA with specific nucleotide bases, proteins made from 20 standard amino acids, and cell membranes built from particular lipid molecules. Alien life might use completely different information storage molecules, different catalysts, different energy currencies. This means alien organisms would likely be incompatible with Earth biochemistry at the most fundamental level. You probably couldn't eat alien food because your digestive enzymes wouldn't recognize the molecular structures. Alien microorganisms might not be able to infect you, but they also might trigger bizarre immune responses because your body has never encountered anything like them. Conversely, Earth microorganisms you carry with you could potentially devastate an alien ecosystem that has no defenses against them. We could become an invasive species on a cosmic scale, accidentally destroying an entire biosphere just by arriving there. This ethical concern is why planetary protection protocols exist, rules designed to prevent contaminating other worlds with Earth life or bringing potentially dangerous alien organisms back to Earth. But let's consider an even more radical possibility. What if we don't try to find habitable planets, but instead build our own worlds in space? This is the concept behind space habitats, enormous structures constructed in space that provide Earth-like conditions inside through rotation-generated artificial gravity, controlled atmospheres, imported water, and artificial lighting. The physicist Gerard O'Neill proposed elaborate designs in the 1970s for cylindrical habitats kilometers long that could house thousands or even millions of people. These O'Neill cylinders would rotate to create artificial gravity on their inner surfaces, You'd live on the inside of a giant spinning tube, with the landscape curving upward around you until it met overhead. Sunlight would be reflected in through massive windows using external mirrors. You'd have parks, farms, cities, all under a carefully controlled environment. It's a breathtaking vision that captures the imagination. But the resources required to build such structures are staggering. You'd need to mine asteroids for metals and minerals, process them into construction materials, transport everything to the construction site, and assemble components on a scale never before attempted. You'd need abundant energy, perhaps from massive solar panel arrays or space-based nuclear reactors. You'd need hundreds or thousands of workers in space for years or decades. One study estimated that building a single large O'Neill cylinder could require processing millions of tons of asteroid material. We currently launch only a few hundred tons of payload into space per year globally. Scaling up to the required level would demand revolutionizing space transportation. And even if we built these habitats, they'd still be artificial bubbles of Earth environment surrounded by the hostile void. A collision with even a small piece of space debris traveling at orbital velocities could puncture the hull catastrophically. Micrometeorite impacts would constantly erode external surfaces, requiring continuous maintenance and repair. The rotating mechanisms would experience wear and tear that could lead to catastrophic failures if not properly maintained. You'd be living in a machine, and machines break down. There's also the question of purpose. Why would millions of people choose to live in artificial habitats when Earth exists? Earth has natural beauty, vast open spaces, weather, oceans, forests, mountains, and ecosystems that have taken billions of years to develop. A space habitat would be an artificial substitute, a carefully maintained simulation of the real thing. Some people might find that appealing, pioneers seeking new frontiers. But would it ever truly replace Earth as humanity's home? Or would it always be seen as a backup, a lifeboat, for when Earth becomes uninhabitable? And that brings us to perhaps the most important question of all. Why do we want to leave Earth in the first place? The usual answer is survival. We fear extinction events, asteroid impacts, supervolcano eruptions, nuclear war, climate catastrophe, pandemics, or some other disaster that could wipe out human civilization or even the entire species. By spreading to other worlds, we create redundancy, insurance against total annihilation. If Earth is destroyed, humanity survives elsewhere. This logic is compelling on the surface, but it overlooks a critical reality. Nothing we might encounter in space or on other worlds is as immediately dangerous to us as we are to ourselves here on Earth. The greatest threats to human survival are human-created. Climate change, nuclear weapons, biological warfare, artificial intelligence gone wrong, environmental destruction, these are all problems of our own making. If we can't solve these problems on Earth, where we have breathable air, liquid water, abundant resources, and a functioning biosphere, how will we solve them in the far harsher environments of space or other planets? Running away to Mars doesn't fix the fundamental challenges of human cooperation, resource management, and long-term thinking. If anything, the scarcity and harsh conditions of space environments would amplify conflicts rather than resolve them. History shows us that when humans face scarce resources and difficult living conditions, tensions rise. Imagine a Mars colony dependent on a single, malfunctioning water recycling system or a failing nuclear reactor. The pressure to survive could bring out both the best and worst of human nature. There's also a deeper philosophical question here. What does it mean to be human in an environment completely divorced from Earth? Our psychology, our cultural references, our sense of beauty, our very identity has been shaped by this planet. We find comfort in blue skies because that's what we evolved under. We crave the smell of rain, the feeling of grass beneath our feet, the sight of trees swaying in the wind. These aren't just preferences, they're deeply embedded in who we are as a species. Children born on Mars or in space habitats would grow up without ever experiencing these things firsthand. They'd know Earth only through videos and virtual reality simulations. Their conception of home would be fundamentally different from ours. Would they still consider themselves human in the same way we do? Or would they become something new, a branch of humanity adapted to alien environments? This isn't science fiction speculation. It's a genuine question about identity and evolution. Given enough time in different environments with different selective pressures, populations diverge. Martian humans might eventually become biologically distinct from Earth humans. Now let's talk about energy, because everything we've discussed so far requires enormous amounts of it. Launching spacecraft, maintaining life support systems, generating artificial gravity, shielding against radiation, producing food and water, powering habitats, all of this demands energy on scales that dwarf our current capabilities. On Earth, we have abundant energy from the Sun, approximately 1,000 watts per square meter at the surface. We have fossil fuels accumulated over millions of years. We have nuclear fuel that can be mined and processed. We have hydroelectric, wind, and geothermal power. In space or on other worlds, your energy options become severely limited. Solar power works well in the inner solar system, but efficiency drops dramatically as you move away from the Sun. Mars receives only about 43% as much sunlight per square meter as Earth. The outer solar system is too dark for solar panels to be practical. That leaves nuclear power as the only viable option for deep space or outer planet missions. But nuclear reactors are heavy, complex, require fuel that must be brought from Earth or processed from local materials if you're lucky enough to find suitable isotopes, and produce radioactive waste that needs to be managed safely for thousands of years. NASA has been developing space nuclear power systems, including fission surface power for lunar and Martian bases and nuclear thermal propulsion for faster transit times. These technologies show promise, but they're still in development stages. A report from 2025 in Physics Today discusses how nuclear fission technologies could enable sustained lunar presence and propel crewed missions to Mars, but acknowledges the enormous technical challenges remaining. The systems must be incredibly reliable because any reactor failure in a space environment could be catastrophic. You can't just shut it down and walk away. You can't call in repair crews from the next town over. Everything must work perfectly, often for years without maintenance. And even with nuclear power, the energy density required for truly ambitious space endeavors like interstellar travel remains far beyond our capabilities. The rocket equation, a fundamental principle of spaceflight, tells us that the amount of fuel needed increases exponentially with the desired change in velocity. To reach even a small fraction of light speed requires fuel masses many times the mass of the payload itself. Chemical rockets are completely inadequate. Nuclear thermal propulsion helps, but still isn't enough. Nuclear pulse propulsion, where you detonate nuclear bombs behind your spacecraft to push it forward, could theoretically reach several percent of light speed, but it would require thousands of nuclear devices and create obvious political and safety concerns. More exotic concepts like antimatter engines offer incredible energy density, but we can currently produce only tiny amounts of antimatter at costs of trillions of dollars per gram. It would take longer than the current age of the universe to produce enough antimatter for a single interstellar mission at current production rates. Fusion drives, powered by the same nuclear fusion reactions that power stars, remain frustratingly out of reach despite decades of research. We've achieved fusion in laboratory conditions and in experimental reactors, but sustained, energy-positive fusion that could power spacecraft remains elusive. Then there are the truly speculative concepts, warp drives that bend space-time to move faster than light without technically violating relativity, wormholes that create shortcuts through space, generation ships that travel for centuries, or even the idea of sending human consciousness rather than bodies, uploading minds into machines or transmitting information to be reconstructed at the destination. These ideas make for compelling science fiction, but they're so far beyond our current understanding of physics and biology that we can't meaningfully assess their feasibility. The Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994, theoretically allows faster-than-light travel by contracting space in front of a spacecraft and expanding it behind. But it requires exotic matter with negative energy density, something that probably doesn't exist in the quantities needed. Recent calculations suggest it would require the mass energy of entire planets or even stars. Even if we could somehow gather that much energy, we don't know how to create or manipulate exotic matter. The same limitations apply to wormholes, which would require similar exotic matter to keep them open and stable. As for uploading consciousness, we don't yet understand consciousness well enough to know if it's even theoretically possible to transfer it from biological brains to electronic substrates. We don't know if the pattern of neural connections that makes you who you are could survive such a transfer, or if you'd simply create a copy while the original you dies. These are profound philosophical questions that don't have clear answers. And even if we solved them, you'd still need physical infrastructure at your destination to receive the transmitted information and reconstruct or embody it somehow. Let's bring this back to a more immediate concern, the economic reality. Space exploration and colonization are extraordinarily expensive. The International Space Station, humanity's only permanent outpost beyond Earth, cost roughly $150 billion to build and maintain over 2 decades. It orbits just 400 kilometers above Earth's surface, close enough that resupply missions take only hours, and emergency evacuations back to Earth are possible within minutes. It houses typically 6 to 7 crew members. Scaling up to permanent settlements on the Moon or Mars, housing hundreds or thousands of people, would cost trillions of dollars. Where would this funding come from? Government space budgets represent tiny fractions of national spending. NASA's budget is currently about 0.5% of the United States federal budget, roughly $25 billion annually. The European Space Agency, Roscosmos, CNSA, ISRO, and other space agencies have similar or smaller budgets. Combined global space spending by governments is perhaps $80 to $100 billion per year. That sounds like a lot until you realize that's less than what's spent globally on pet food or cosmetics. Private space companies like SpaceX, Blue Origin, and others have brought new energy and innovation to the field, but they still depend heavily on government contracts and face the same fundamental physical and economic constraints. SpaceX's Starship, the largest and most powerful rocket ever built, is designed to reduce launch costs through reusability. That's a crucial innovation, but even dramatically cheaper launch costs don't eliminate the fundamental challenges we've discussed. Physics doesn't negotiate. Biology doesn't offer discounts. Distance remains distance regardless of how efficiently you launch your rockets. Some proponents argue that asteroid mining could provide the economic incentive for space expansion. Asteroids contain valuable metals like platinum, gold, and rare earth elements. A single large metallic asteroid might contain more platinum than has ever been mined on Earth. The total mineral wealth of the asteroid belt has been estimated in the quadrillions of dollars. If we could access those resources, the argument goes, space colonization would pay for itself and generate enormous wealth. But this logic has a fundamental flaw. The value of those metals is based on their scarcity on Earth. If you suddenly flood the market with asteroid-sourced platinum, the price crashes. The economic value disappears precisely when you succeed in extracting the resources. You can't become wealthy by making valuable things worthless. The real value of asteroid resources would be for use in space itself, to build spacecraft and habitats without having to launch materials from Earth's deep gravity well. But that only makes economic sense if you already have a large infrastructure and population in space that needs those resources. It's a chicken and egg problem. You need a space economy to justify asteroid mining, but you need asteroid mining to enable a space economy. Furthermore, the technical challenges of asteroid mining are immense. You need to identify suitable asteroids, which requires extensive survey missions. You need to send mining equipment to these asteroids, which are often irregularly shaped objects with barely any gravity to hold things down. You need to extract materials in conditions unlike anything on Earth, process them into usable forms, and transport them to where they're needed. Each step introduces complexity, cost, and points of failure. Several companies have attempted to start asteroid mining ventures over the past decade. Most have failed or pivoted to other business models because the technical and economic hurdles proved insurmountable with current technology. Let's consider another angle, the Fermi paradox. This famous question asks, if intelligent life is common in the universe, where is everybody? Our galaxy contains hundreds of billions of stars. Many of these stars have planets. Some of those planets should be habitable. Life arose relatively quickly on Earth once conditions allowed. Intelligence eventually evolved here. If this is a typical pattern, the galaxy should be teeming with intelligent civilizations, some of them millions or billions of years older than us. Yet we see no evidence of them. We detect no alien radio signals, no megastructures harvesting stellar energy, no signs of astroengineering projects reshaping solar systems, no colony ships arriving in our neighborhood. The silence is deafening. Many solutions to the Fermi paradox have been proposed. Perhaps life is rare, perhaps intelligence is rare, perhaps civilizations destroy themselves before achieving interstellar travel, perhaps they're out there but hiding from us or ignoring us. Or perhaps, and this is the possibility we're exploring here, interstellar colonization is simply too difficult. The barriers we've discussed aren't unique to humans. Any biological intelligence would face similar constraints of distance, energy, radiation, and the fundamental incompatibility between evolved life and the space environment. Maybe we don't see galaxy-spanning civilizations because they don't exist and can't exist. Maybe every intelligent species hits the same wall we're hitting. They achieve spaceflight, they explore their local planetary neighborhood, they realize that leaving their home star system is prohibitively difficult, and they either stay home or go extinct. This is sometimes called the Great Filter, a challenge so difficult that it prevents civilizations from spreading across the galaxy. If the Great Filter is behind us, something in our evolutionary past that most life doesn't survive, then we're incredibly lucky and might have a real chance at a cosmic future. But if the Great Filter is ahead of us, if it's the transition from single-planet species to multiplanetary or interstellar species, then we might be doomed to the same fate as every other civilization that's tried and failed. There's a certain humbling perspective that comes from this realization. For most of human history, we saw ourselves as the center of everything. We thought Earth was the center of the universe, with everything revolving around us. Copernicus showed us we orbit the sun. We learned that our sun is one star among hundreds of billions in our galaxy. We discovered that our galaxy is one among hundreds of billions in the observable universe. We're not special cosmically, we're not privileged. We're a species of clever primates on a small rocky planet orbiting an average star in an ordinary galaxy in an unremarkable region of space. And yet, this pale blue dot, as Carl Sagan called it, is everything to us. Every human who has ever lived, every civilization that has risen and fallen, every work of art, every scientific discovery, every moment of love and suffering, all of it happened here on this fragile world, suspended in a sunbeam. Earth is our home in a way that nowhere else can ever be. It's not just the place where we happen to live, it's the place that made us, that shaped us, that contains the entire story of life's evolution from single cells to conscious beings capable of wondering about our place in the cosmos. Maybe the real lesson isn't that we need to leave Earth, but that we need to protect it. The resources we'd spend trying to terraform Mars could instead be used to repair Earth's ecosystems. The engineering expertise we'd need to build space habitats could be applied to creating sustainable cities here. The international cooperation required for interstellar missions could start with solving problems like climate change, poverty, and conflict on our home planet. We have one world that we know for certain can support human life. Preserving that world might be more important than trying to create new ones. This doesn't mean we should abandon space exploration. Far from it. Understanding the universe is one of the noblest pursuits of humanity. Robotic probes can explore places humans can't safely go. Telescopes can reveal cosmic wonders billions of light years distant. Scientific research in space advances our knowledge and occasionally produces practical benefits. The technologies developed for space missions often find applications on Earth. Satellite communications, weather forecasting, GPS navigation, medical imaging devices, water purification systems, and countless other innovations trace their roots to space programs. Moreover, there's something transcendent about looking outward, about asking big questions and pursuing answers even when they're difficult to find. The night sky has inspired humans since we first looked up and wondered what those points of light might be. That sense of wonder, that curiosity about our place in the grand cosmos is part of what makes us human. We should nurture it, encourage it, and continue exploring within our capabilities. But we also need to be realistic about those capabilities and honest about the limitations we face. The universe is vast beyond human comprehension. The distances are too great. The environments are too hostile. Our biology is too specifically adapted to Earth conditions. The energy requirements are too enormous. The time frames are too long. These aren't problems that better technology will necessarily solve because they are not just technological problems. They're fundamental constraints imposed by physics and biology. Perhaps the answer lies not in leaving Earth physically, but in understanding that we're already part of something larger. The atoms in our bodies were forged in the hearts of dying stars billions of years ago. We are quite literally made of stardust. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it came from stellar nucleosynthesis, from the fusion reactions that power stars and the supernova explosions that scatter those elements across space. We're not separate from the cosmos. We're an intrinsic part of it, a way for the universe to know itself. As Sagan beautifully expressed, every time you look up at the stars, you're looking back in time. The light reaching your eyes left those stars years, centuries, or even millennia ago. When you gaze at the Andromeda galaxy, visible to the naked eye on a dark night, you're seeing light that began its journey 2.5 million years ago, when our ancestors were just learning to use stone tools. You're witnessing the past directly. In a very real sense, astronomy is time travel, a way to observe the history of the universe written in light. And what a history it is! The universe began approximately 13.8 billion years ago in the Big Bang, an expansion from an incredibly hot, dense state. In those first moments, only the simplest elements existed: hydrogen, helium, and traces of lithium. The first stars formed from these primordial gases about 100 million years after the Big Bang. These population 3 stars, as astronomers call them, were massive and short-lived. They burned brilliantly and died quickly in supernova explosions that scattered heavier elements into space. Subsequent generations of stars incorporated these heavier elements. They formed planets around them. Chemistry became more complex. On at least one planet orbiting an unremarkable yellow dwarf star, conditions allowed molecules to organize themselves into self-replicating patterns. Life emerged. Over billions of years, that life evolved, diversified, and eventually produced conscious beings capable of understanding the very process that created them. That's us. We're the universe contemplating itself. This perspective shift is profound. Instead of seeing ourselves as trapped on Earth, desperate to escape, we can see ourselves as an extraordinary flowering of cosmic evolution. Earth isn't a prison. It's a sanctuary, a rare jewel where conditions align precisely to nurture and sustain the complex chemistry of life. The very things that make space deadly, the vacuum, the radiation, the temperature extremes, serve to protect our biosphere by creating a barrier that shields us from most cosmic threats while still allowing us to observe and study the universe. Consider the exquisite balance required for Earth to be habitable. We orbit at just the right distance from a stable, long-lived star. Too close, and we'd be scorched like Venus. Too far, and we'd be frozen like Mars. Our planet has sufficient mass to hold an atmosphere, but not so much that we'd retain a crushing envelope of hydrogen like the gas giants. We have liquid water on the surface, a substance with unique properties essential for life as we know it. Water's density anomaly, where ice floats rather than sinks, prevented our oceans from freezing solid from the bottom up during ice ages. Earth has a large moon created by a collision with a Mars-sized body early in our planet's history. This moon stabilizes Earth's axial tilt, preventing extreme climate variations that would occur if our axis wobbled chaotically. The moon also creates tides that helped drive early evolution by creating intertidal zones where organisms faced selective pressure to adapt to both aquatic and terrestrial conditions. Jupiter, the giant planet in our outer solar system, acts as a gravitational shield, deflecting many comets and asteroids that might otherwise impact Earth more frequently. Our planet has a molten iron core that generates a magnetic field, protecting us from solar wind that would otherwise strip away our atmosphere. We have plate tectonics, a geological recycling system that regulates carbon dioxide levels over geological timescales, preventing runaway greenhouse effects or ice ages. Volcanic activity releases gases that replenish the atmosphere. The biosphere itself regulates conditions through feedback loops like how plants produce oxygen that allows animal life, while animals produce carbon dioxide that plants need. All of these factors and countless others had to align for Earth to not only be habitable, but to remain stably habitable for billions of years, while life evolved from single cells to technological intelligence. Change any one of these parameters significantly, and Earth might be lifeless. This is sometimes called the Goldilocks principle. Everything has to be just right. Recent research from missions like Kepler and TESS suggests that while planets in habitable zones might be relatively common, Earth-sized planets with Earth-like conditions might be extremely rare. A 2023 study analyzing data from the James Webb Space Telescope examined the atmosphere of TRAPPIST-1c, an exoplanet orbiting a red dwarf star 40 light-years away. Unlike previous observations suggesting these planets might have atmospheres, the JWST data indicated that TRAPPIST-1c likely has little to no atmosphere, consistent with it being a barren rock. This finding suggests that planets around red dwarfs, the most common type of star, might struggle to maintain atmospheres due to intense stellar activity. If true, this dramatically reduces the number of potentially habitable worlds in the galaxy. Each new discovery seems to reinforce how special Earth is. We keep learning that being in the habitable zone isn't enough. You need the right kind of star, not too variable, not too prone to flares. You need the right planetary mass, composition, and magnetic field. You need protection from impacts. You need geological activity to recycle nutrients, but not so much that the surface is constantly destroyed. You need water delivered in the right amounts at the right time in the planet's history. You need the right atmospheric composition maintained over billions of years. The list of requirements keeps growing. This brings us to what some scientists call the rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Donald Brownlee in their book published in the year 2000. They argue that while simple microbial life might be common in the universe, complex life, and especially intelligent life, might be extraordinarily rare. The conjunction of factors required is so specific that Earth-like planets capable of sustaining complex ecosystems for billions of years might be vanishingly uncommon. If they're right, if planets like Earth are truly rare, then our responsibility to preserve this world becomes even greater. We might be one of the only places in the entire galaxy where life has achieved consciousness and developed the capacity to understand the universe. That makes us precious beyond measure. It means that when we look out at the stars, we're not just seeing distant suns, we're seeing a universe that, for the most part, is unaware of itself. We're the exception, the rare places where matter has organized itself sufficiently to observe, understand, and appreciate the cosmos. But rarity doesn't equal loneliness. Even if technological civilizations are scattered and rare, the universe itself is anything but empty. Space teems with phenomena of breathtaking beauty and complexity. We've observed stellar nurseries where new stars are being born, regions like the Eagle Nebula's pillars of creation, where clouds of gas and dust collapse under gravity to ignite nuclear fusion. We've witnessed the deaths of stars, from the gentle planetary nebulae cast off by sun-like stars at the end of their lives, to the violent supernova explosions that outshine entire galaxies for weeks. We've detected neutron stars, the collapsed cores of massive stars, spinning hundreds of times per second and generating magnetic fields trillions of times stronger than Earth's. We've confirmed the existence of black holes, objects so dense that not even light can escape their gravity, from stellar mass black holes a few times heavier than the Sun to supermassive monsters, billions of times the Sun's mass, lurking at the centers of galaxies. The Event Horizon Telescope collaboration produced the first direct images of black holes, capturing the shadow of the supermassive black hole in the galaxy Messier 87 in 2019 and our own galaxy's central black hole, Sagittarius A star, in 2022. We've observed the collision of neutron stars, events that create gravitational waves, ripples in spacetime itself that were detected by LIGO and Virgo observatories. These collisions also produce gamma-ray bursts, the most energetic explosions in the universe since the Big Bang, and forge heavy elements like gold and platinum through rapid neutron capture. The gold in your jewelry, the platinum in your electronics, they were likely created in one of these cataclysmic mergers billions of years ago. We've discovered that galaxies themselves are organized into vast structures, clusters, superclusters, and filaments separated by enormous voids. The universe has a cosmic web structure, with matter concentrated along filaments, surrounding nearly empty voids hundreds of millions of light-years across. This structure formed from tiny density fluctuations in the early universe, amplified over billions of years by gravity. We can observe this evolution by looking at distant galaxies, seeing the universe as it was billions of years ago when it was younger and more chaotic. We've learned that the ordinary matter we're made of, protons, neutrons, electrons, everything we can see and touch, comprises only about 5% of the universe's total mass energy. About 27% is dark matter, invisible material, that we detect only through its gravitational effects on visible matter and light. The remaining 68% is dark energy, a mysterious force causing the universe's expansion to accelerate. We don't know what dark matter or dark energy actually are. They're among the biggest unsolved mysteries in physics. Think about that for a moment. We understand only 5% of what the universe is made of. 95% remains mysterious. This should inspire humility about our place in the cosmos and excitement about how much we still have to learn. Every answer we find raises new questions. Every mystery we solve reveals deeper mysteries beneath. The universe is far stranger and more wonderful than we imagined, and our understanding, while impressive, remains incomplete. This is why we explore, why we build telescopes and send probes to distant worlds, not because we expect to colonize them, but because understanding the universe is intrinsically valuable. Knowledge doesn't need to be immediately practical to be worthwhile. When we study exoplanets, we're not just looking for future homes. We're learning about how planetary systems form and evolve, testing our theories of astrophysics and understanding our own planet's history by seeing it in the context of countless other worlds. When we send rovers to Mars, we're not just preparing for colonization, we're investigating whether life ever existed beyond Earth, a question with profound implications for biology and philosophy. If we find evidence that life arose independently on Mars, even just simple microbes, it would suggest that life might be common in the universe. If we find no evidence despite thorough searching, it might indicate that even simple life is rare, making Earth even more precious. Either answer would be scientifically revolutionary. The Perseverance rover, currently exploring Mars's Jezero crater, is collecting samples from what was once an ancient lake bed. These samples might contain signs of past microbial life, if any ever existed there. NASA plans to return these samples to Earth in the early 2030s through the Mars Sample Return mission, one of the most ambitious robotic missions ever attempted. It requires multiple launches, a Mars ascent vehicle, an orbital rendezvous, and a safe return to Earth, all autonomously coordinated across millions of kilometers. If successful, scientists will have pristine Martian rocks to analyze with laboratory instruments far more sophisticated than anything we can send to Mars. But notice what this represents. We're bringing samples back to Earth for study, not sending humans to Mars to study them there. This makes scientific and economic sense. Robotic missions cost a tiny fraction of crewed missions and can take risks that would be unacceptable with humans aboard. The Curiosity rover, operating on Mars since 2012, cost about $2.5 billion for development, launch, and operations. Estimates for a crewed Mars mission typically start at $100 billion and go up from there. For the cost of one crewed Mars mission, we could send dozens of advanced robotic missions to Mars, the outer planets, asteroids, comets, and even interstellar space. The Voyager spacecraft, launched in 1977, have now left the heliosphere and entered interstellar space, still sending back data about the boundary between our Sun's influence and the galactic environment beyond. They're the most distant human-made objects, over 20 billion kilometers away, still functioning after nearly 50 years. These missions cost a fraction of what crewed missions would require, and have returned scientific value far beyond their expense. The images Voyager 2 captured of Neptune in 1989 remain the only close-up views we have of that distant ice giant. More recently, the New Horizons mission flew past Pluto in 2015, revealing a geologically active world far more complex and interesting than anyone expected. Pluto has nitrogen glaciers, water ice mountains, a multi-layered atmosphere, and possible subsurface oceans. In 2019, New Horizons flew past Arakoth, a contact binary Kuiper Belt object, providing our first close look at a pristine remnant from the solar system's formation. These discoveries came from a spacecraft weighing less than 500 kilograms. Sending humans to the outer solar system would require spacecraft millions of times more massive, with correspondingly greater costs and risks. The pattern is clear. For scientific exploration, robots are superior to humans in almost every way except adaptability and intuition. They don't need life support, food, water, or radiation shielding. They don't suffer psychological effects from isolation. They can be sent on one-way missions. They can hibernate during long transits to conserve power. They can operate in environments that would instantly kill humans. As artificial intelligence and robotics improve, the gap in adaptability narrows while the advantages of robotic exploration grow. Current AI systems can now perform increasingly complex tasks autonomously. The Mars Ingenuity helicopter, which has made dozens of flights in Mars's thin atmosphere since 2021, navigates autonomously because the communication delay makes real-time, remote control impossible. Future spacecraft might use AI to analyze their surroundings, make decisions about where to explore next, and even repair themselves without constant human oversight. This could enable exploration of places like Titan, Saturn's largest moon, where the communication delay of over an hour makes traditional teleoperation impractical. Titan is particularly fascinating because it's the only moon in our solar system with a substantial atmosphere, thicker than Earth's. It has liquid methane and ethane lakes and seas on its surface, weather patterns with methane rain, and complex organic chemistry occurring in its atmosphere and on its surface. Some scientists speculate that Titan might have exotic forms of life based on liquid methane instead of water. The Dragonfly mission, currently planned for launch in 2027 and arrival in 2034, will send a nuclear-powered drone to fly across Titan's surface, exploring diverse locations and searching for signs of prebiotic chemistry or even life. This is exploration in the grand tradition, using our technology to extend our senses to places we cannot go ourselves. It mirrors how we explore Earth's most hostile environments. We don't send humans to live permanently at the bottom of the Mariana Trench or in the heart of Antarctica's interior, even though those places are vastly more hospitable than anywhere beyond Earth. We send instruments, we visit briefly with extensive support, and we study these environments to understand how our planet works. The same approach makes sense for space. There's also a psychological and cultural dimension to consider. The images and data from space missions don't just advance science. They inspire wonder, shift perspectives, and unite humanity in shared discovery. The photograph Earthrise, taken by Apollo 8 astronauts in 1968, showing Earth rising above the Moon's horizon, became one of the most influential environmental images ever created. It viscerally demonstrated our planet's isolation and fragility in a way that no words could capture. Many environmentalists cite that image as awakening their awareness of Earth's uniqueness and vulnerability. Similarly, the pale blue dot image taken by Voyager 1 in 1990 at Carl Sagan's request, showing Earth as a tiny speck suspended in a sunbeam, has inspired countless people to think differently about our place in the cosmos. These images have cultural value far beyond their scientific content. They change how we see ourselves. They make abstract concepts tangible. They remind us that we're all passengers on this small world, that our differences are trivial compared to the vast indifference of space, that we need to take care of our home because there is nowhere else to go. This brings us back to the central question. If we can't practically leave Earth permanently, what should we do instead? The answer, I believe, is to redirect our energy, resources, and ambition towards solving the challenges we face here. Climate change, biodiversity loss, resource depletion, pollution, poverty, inequality, conflict, these are not insurmountable problems. They're difficult, certainly, but they're orders of magnitude easier than terraforming Mars or building O'Neill cylinders. And unlike space colonization, solving these problems would benefit billions of people alive today, not hypothetical future generations. Climate change is perhaps the most pressing challenge. Human activities, primarily burning fossil fuels and deforestation, have increased atmospheric carbon dioxide concentrations from about 280 parts per million before the Industrial Revolution to over 420 parts per million today. This is driving global temperature increases, sea level rise, ocean acidification, changing precipitation patterns, and more frequent extreme weather events. The consequences will affect every human on Earth, with the poorest and most vulnerable populations suffering disproportionately. But we know how to address climate change. We need to transition from fossil fuels to clean energy sources: solar, wind, nuclear, and hydroelectric power. We need to increase energy efficiency in buildings, transportation, and industry. We need to protect and restore forests and other ecosystems that absorb carbon dioxide. We need to develop sustainable agriculture that produces food without destroying ecosystems. We need to redesign our cities to be more livable and less dependent on cars. None of this is science fiction. The technologies exist. What's needed is political will, international cooperation, and sustained investment. The same resources we'd spend on Mars colonization could transform Earth's energy systems. $100 billion could deploy enormous amounts of renewable energy, fund research into better batteries and energy storage, upgrade electrical grids, and subsidize electric vehicles. It could protect vast areas of rainforest, restore degraded ecosystems, and fund sustainable development in poorer countries. The return on investment, measured in lives improved and disasters averted, would be immediate and tangible. Biodiversity loss is another crisis that receives insufficient attention. We're currently in the midst of what scientists call the sixth mass extinction, the first caused by a single species: us. Species are going extinct at rates 100 to 1,000 times higher than the natural background rate. We've destroyed or degraded over half of Earth's forests, wetlands, and grasslands. Ocean ecosystems are collapsing from overfishing, pollution, and warming waters. Insect populations are plummeting, threatening the pollination services that much of our food production depends on. This isn't just an aesthetic or moral issue, although those dimensions matter too. Biodiversity provides essential ecosystem services: pollination, water filtration, soil formation, climate regulation, and countless others. Many medicines come from natural compounds discovered in plants, fungi, and animals. Genetic diversity in wild crop relatives provides traits that could help us adapt agriculture to changing conditions. When we lose species, we lose potential solutions to problems we haven't even encountered yet. We're burning down the library of life before we've read most of the books, but again, we know how to address this. We need to protect remaining wild areas through expanded parks and reserves. We need to restore degraded ecosystems, allowing forests to regrow and wetlands to recover. We need to reform agriculture to be less destructive, reducing pesticide use and creating wildlife corridors between protected areas. We need to reform fishing practices to allow depleted fish stocks to recover. We need to address pollution, particularly plastics in the ocean and chemicals that disrupt ecosystems. All of this is achievable with existing knowledge and technology. Resource depletion and pollution are interconnected challenges. Our current economic system treats Earth's resources as infinite and its capacity to absorb waste as unlimited. Neither is true. We're extracting minerals, timber, fish, and fresh water faster than they can regenerate. We're producing waste faster than natural systems can break it down. Plastic pollution now permeates every environment on Earth, from the deepest ocean trenches to the peak of Mount Everest to human bloodstreams. Microplastics have been found in human placentas, lungs, and blood. The long-term health effects remain unknown, but they're unlikely to be positive. The solution is a transition to a circular economy where materials are reused, recycled, and regenerated rather than extracted, used once, and discarded. This requires redesigning products for durability and recyclability, developing better recycling technologies, reducing consumption of unnecessary goods, and shifting from ownership to service models where it makes sense. Some countries and cities are already moving in this direction. The Netherlands has set a goal of becoming fully circular by 2050. Many European countries have implemented extended producer responsibility laws that require manufacturers to handle their products at end of life, incentivizing better design. Technology can help with all of these challenges. Advances in materials science can create biodegradable alternatives to plastics. Precision agriculture can increase food production while reducing environmental impact. Lab-grown meat and plant-based alternatives could reduce the enormous environmental footprint of animal agriculture, which currently uses about 80% of agricultural land while providing only 18% of calories. Vertical farms and aquaponics could produce food in urban areas with minimal land and water use. Better batteries and energy storage could make renewable energy more reliable and widespread. But technology alone isn't enough. We also need social and political changes. We need economic systems that account for environmental costs instead of treating them as externalities. We need to shift away from the ideology of endless growth on a finite planet. We need to address inequality both within and between countries because environmental protection is difficult when people are struggling to meet basic needs. We need education systems that teach ecological literacy and systems thinking. We need media that accurately communicate scientific findings without false balance or sensationalism. Most importantly, we need to reconnect with nature. Many people, especially in urban areas, live almost entirely in human-created environments. They experience nature only through screens or occasional visits to parks. This disconnection makes it psychologically easier to ignore environmental destruction. When you directly experience wild places, when you understand that you're part of ecosystems rather than separate from them, environmental protection becomes personal rather than abstract. There's emerging research on the mental health benefits of nature exposure. Time spent in natural environments reduces stress, anxiety, and depression. It improves attention, creativity, and cognitive function. Children who grow up with regular nature exposure show better physical and mental health outcomes, yet modern life increasingly separates us from the natural world. We spend over 90% of our time indoors. Children have less free outdoor playtime than any previous generation. This nature deficit, as author Richard Louv calls it, has consequences for both human well-being and environmental values. Reconnecting with nature doesn't require dramatic lifestyle changes. It can be as simple as spending more time in parks, tending a garden, observing birds, or taking walks in natural areas. Cities can be designed to incorporate more green space, street trees, and urban forests. Schools can include outdoor education and nature-based learning. Even small doses of nature contact seem to provide benefits. A study from 2019 found that people who spent at least 2 hours per week in nature reported significantly better health and well-being, with benefits plateauing around 5 hours per week. If this deep dive into humanity's cosmic limitations fascinated you, you need to watch the video on the screen. Reveals the devastating truth about interstellar travel that even optimistic scientists won't tell you. We're talking about physics so unforgiving that humanity will never reach another star system. See you there.